everyone. My name is Alexander Kuzmenko. I work for Yandex as a developer of ClickHouse, and ClickHouse is a topic of our Meetup. So now I will be giving a short introduction into what it is. So probably you know that ClickHouse is an open source analytical database, but it would be interesting to know if somebody of you tried to use it. Oh, great, that's a fair number. I hope after our talk there will be motivation for this number to increase. This talk refers to lots of features of ClickHouse, and you can download these slides on this link. And the slides themselves have links to documentation or like blog posts so that you can read in depth if anything interests you. So what is ClickHouse? As I said, it is a relational database management system that is geared towards the analytical workloads. It's free and open source. It's published under Apache 2.0 license, so you can use it for any purpose and even modify it. And as a query language, it uses a normal SQL. It is a relational database, so data is management in tables. It's built for both vertical and horizontal scaling. So it uses all the resources of a server by parallelizing computation, and it also scales seamlessly to a multi-server installation. So you can, it has replication features, and you can build a resilient system that is tolerant up to a single data center failure. It scales linearly, well into the hundreds of servers and hundreds of billions or even thousands of billions records daily. And the distinctive trait we often mention is that it's surprisingly fast. And this fact is very important because having being able to get an answer to a query very fast changes the way you work with data. So it allows you to explore your data interactively, test your hypothesis faster, and you can make much more progress in this fashion. So you're probably wondering, what is this Yandex company? Yandex is a major Russian search engine. In Russia, it's more popular than Google, and it also has a web analytics solution. It's called Yandex Magica. It's similar to the Google Analytics, and it is a very big installation. It processes like 30 billion rows daily. All the data combined are 3 petabytes compressed, and the biggest cluster is like 700 machines. And on this cluster, it reaches processing speed about 2 terabytes per second. So this system is about 10, probably years old. No, I think even older. So before, like in the beginning of 2000, it used a MyESAM solution. So it needed heavy pre-aggregation, and it didn't scale well for the growing world. The throughput was limited, and it only could show you some predefined reports. So like when your user sees an interface of this web analytics app, they can't select what they want to see, they only can choose from some predefined reports. And it was not real time. So the data was added like once a day. So because of these limitations, Yandex Magica started to think about moving to different databases. They evaluated various solutions, and in the end, they decided to build their own. And this is how like proper ClickHouse started in 2009. When it was built, it was found that it works very good, and it enabled Yandex Magica to build, as they call it, double real-time reporting. What does this mean? The system adds new events, new user actions are added in real time, and they are reflected in the report instantly. And secondly, you can build custom reports also in real time. So you can click what you want to do, no pre-aggregation, everything is calculated over the raw data, and it's very fast. So you can work with this interactively. After this success, ClickHouse became the main engine of Yandex Metrica in 2012, and it was open sourced in 2016. So first of all, it gained a wide adoption inside Yandex, because Yandex employs lots of business analysts who make business decisions by analyzing the various statistics and data. And so Yandex has a in-house MapReduce system. It's good, but it's not real-time. And this was as a real-time solution, ClickHouse became very popular. And then, after it was open sourced, it was slowly adopted by thousands of companies worldwide. Lots of users of ClickHouse use it for the case that is similar to its original purpose, for ad tech, for clickstream aggregation, and it is also used for geospatial processing, for fraud detection, monitoring, logs, etc. You can read about adoption at our site. And also it has some curious application, like it was once used to process a part of data for CERN LHCb particle physics experiment, for some bioinformatic cases, and blockchain transaction history, whatever. So what is common of these cases, and when should you use ClickHouse? Its main use case is when you have a stream of well-structured and mutable events. So you only append data and don't modify it, so no updates. Your data mostly has fixed schema. There is a provision to support like schema-less data. You can put JSON in, or there is a special nested type for like key value storage. But some part of your schema should be fixed. So append only, no updates. There is a function that allows you to modify your data, but it is a heavyweight operation that is not used in normal operation of the database. You can use it to comply with some data regulations, for example. So you have this kind of data, and over this data you need to build flexible real-time reporting. ClickHouse allows you to do this because queries finish in seconds, not in hours, like they could in some more traditional big data solution. You don't need any pre-aggregation, pre-processing, because it is fast enough over the raw data. And it enables you to perform some ad hoc experiments and test hypotheses more often. Also, there are some cases when you shouldn't use ClickHouse. It's not suitable for transactional processing because it has no transactions. Single insert is atomic, but we don't have cross-table atomicity, cross-query atomicity, and our updates are very heavy. ClickHouse is not suitable if you need key value storage. So if you have to retrieve only a single record, ClickHouse has to read lots of data because it uses sparse indexes to save space. So it only can read data in bulk. It's not suitable for document or blob storage because the architecture is optimized for records less than 100 kilobytes. And it's not suitable for working with highly normalized data. So if you have lots of tables that are connected by foreign keys, and then you do a lot of join, ClickHouse doesn't like this. It's geared towards a more typical analytical schema where you have a wide fact table and lots of small dimension tables. I've been saying that ClickHouse is fast, but how fast exactly? There are a lot of benchmarks, but we like to refer to a nice set of independent benchmarks by Mark Litvinchik. He uses 1 billion taxi rides benchmark. This is 1 gigabyte of records, 50 gigabytes on compressed CSV, 51 columns. And he performs some simple analytical queries on this data. So these three queries, first two queries are just grouped by with some simple analytical functions, and the fourth also has sorting. So what do we have here? First, also I have to say that the hardware is different, so you can't compare directly. It's only to give you an idea of the order of magnitude of what you can expect. So this first thing that is like orders of magnitude faster than everything else is a GPU database running over some crazy GPU cluster. So this is like the top limit of what is possible. Next we have KDB over, again, a pretty big machine, Xeon Phi. I think it has hundreds of cores or something like that. Then a couple of ClickHouse installations, one on a larger cluster and one on a more prone processor. It's interesting to note that BrightLightDB, this GPU database, ClickHouse on some installations can be even faster than a GPU-based database. Then you have a couple of cloud solutions, Redshift from Amazon and BigQuery from Google. Then you have a big data solution, Spark, and another proprietary columnar analytical database, Vertica. So the basic idea that you can get from this table is that ClickHouse indeed is fast, it's competitive to our system, and one of our defining features is that it's free and open source. So from these solutions, only Spark is also open source. All other solutions are proprietary. So you can reach surprisingly good results on a commodity hardware and without paying for licenses. So what allows it to be fast? This is a result of careful architectural decisions. Basically, there are two ways to be faster. You have to read less data and process data faster. To read less, ClickHouse stores the data in a primary key order, so your data is ordered by disk, and then you have sparse skip index that allows you to skip the chunks of data based on the primary key values. And it also has secondary indexes for when you need to filter by some other columns that are not primary key. And it makes heavy use of compression, because with modern CPUs, you should always compress your data. It will be faster, almost in any case. And to process data faster, we use parallel processing, both on a single machine. So your query is going to scale to use all the cores of your server, and distributed queries that are processed on the entire cluster. And the computations we make are themselves very efficient. So, for example, we have more than 40 different group by algorithms. We have vectorized query execution engines that make use of single instruction, multiple data features, and so on. Okay, so I hope you are interested in trying it now. How can you deploy ClickHouse? It is actually pretty simple. We have repositories for major Linux distros. We have Docker containers, and it may be even simpler because ClickHouse is a one binary. So one binary, no dependencies. I think it depends on libc now, right?
But quite old version is required.
Yeah, so you can just download it and it is all in one binary. If you want to have replication, you'll have to configure zookeeper, but if you don't, you don't. You can even test it on your laptop because the same server runs with minimal resources. So it's easy to try. We strive to publish a stable release every 2 weeks. This is possible because we have an extensive suite of automated testing that tests real scenarios. And it is easy to upgrade because no data migration is needed. So you can just run a new version of server and it works with all data, and in this way you can upgrade your cluster replica after replica. Okay, so how do you put data in? With plain inserts. As a format of input data, we support like plain text formats, all kinds of them. We support popular big data formats like Parquet, ORC, etc. I think we can, it's in development probably, but we have a format that can parse regular expression, and we already have in our stable versions the format to which you can specify like the template of your log files, and it's going to parse them into columns. So it's pretty versatile. There is a thing to know that for optimal performance of insert, you need to buffer them. So ClickHouse is optimized for about 1 insert per second. So you have to batch. You can do more, like up to 1,000, but the performance will be not so good. So people use batching. There is a built-in solution for batching as a buffer table. Also, people use Kafka, or there are some third-party solutions. After you have populated your tables with data, what can you do with them? You can query them using a rich dialect of SQL. It's strongly typed. It has a support of higher order functions like array map, where you can write a lambda function inside your query. It has a big variety of aggregate functions that calculate various statistical features. You can do linear regression, quantile, cardinality estimators, etc. It has support for sampling, so you can process a part of table, or you have special approximate quantile functions that work faster, etc. You can store key value records in rows using nested type, and you can apply all cardinality type for dictionary encoding. ClickHouse is supported by lots of BI tools such as Tableau or Apache Superset, and in general we have ODBC and JDBC drivers, so any tools that uses ODBC or JDBC can work with ClickHouse. Personally, my favorite thing about ClickHouse, my favorite tools that I use a lot is ClickHouse Local. It allows you to run ClickHouse queries just on a data file, so you don't have to install a server. You can just specify, so read from file, or you could write here like read from S3 or read from HDFS, and then you write a SQL. So you specify also the structure of this file, and you do some looping query, and it works pretty fast. You can see here that even over a text file, it achieves 1.5 gigabyte per second processing speed. So it is going to be much faster if you use a real server and that uses proper data format. But for experiments, this is great. Or for preparing your data, like an alternative to SED and AFK and etc. to Unix tools, you can use ClickHouse. We have a wide variety of interfaces to connect both to ClickHouse and from ClickHouse to different systems. So to connect to ClickHouse, you can use its native protocol. It has drivers for Python, Go, etc. It has a RESTful HTTP server. It has ODBC, JDBC drivers. It even supports MySQL via protocol. So the tools that can work with MySQL can seamlessly work with ClickHouse or MySQL protocol. And it has some integration to Postgres. To read data from ClickHouse inside of Postgres, you have ClickHouse DB and PG2CH for logical replication. I think we even have the author of PG2CH. Okay, and to connect from ClickHouse to somewhere, you can just open files. You can go to HDFS to open files from there. You can go to S3. You can go to arbitrary URLs with GET requests. You can go to MySQL over MySQL protocol, also ODBC, JDBC, and over all these kinds of things, you can also use a caching layer called external dictionaries. This is when the table is cached on ClickHouse side, so that it doesn't go to it. Okay. So this was a very rough and fast overview of ClickHouse. You can read more in the docs at our site. Also, we have YouTube channels where I hope it's being recorded now. GitHub, Stack Overflow, so lots of resources to get in touch and discuss your cases or maybe some problems. I think now it would be interesting to listen to your questions or maybe discuss some cases where you use ClickHouse or where you are evaluating ClickHouse. So I'd like to hear your questions, and we are giving this ClickHouse t-shirts to people who ask.
Motivation.
Yeah, you have motivation. Yes, please.
Yes, I have a
Ivan, do you know about Power BI?
Those tools are connected via ODBC, so they don't usually have like native support, but usually they generate some generic SQL and have support for ODBC. And given ClickHouse has ODBC driver, it's possible to connect them. So we are not really doing this often internally, but there are like people out there who actually do it and pretty happy with it.
used it in fraud scenarios.
Sorry?
You mentioned you have used it for fraud detection.
Fraud detection.
Yes.
Yeah, I think there
some
are
people do.
a couple of companies who use it for fraud detection. Probably inside Yandex it is used for fraud detection as well, right? Oh, it's in DA. Okay. You didn't hear this.
An example you can give us of this scenario.
Guys, do you know some particular case?
Well, basically you can put like events that happen with your users or clicks or whatever, for, like transactions, if it's like banking or finance. You can put it in ClickHouse, and you can like build like aggregates over like some windows of time, recent events for a particular person, and make a decision on the fly. So ClickHouse queries usually happen in milliseconds. So usually it's good, fast enough to like make a decision on the fly. So like when like someone clicks somewhere or pushes like I buy this, you can decide if it's fraud or not. So unlike other like systems that usually take minutes, which is not acceptable.
One of our early adopters, Cloudflare, it basically uses for a sort of fraud detection. So it uses it to tell bots from normal DNS requests. So I don't know the specifics. Maybe I have a link to a blog post here in the slides. So maybe it's written about the specifics. But in general, it's basically the same as clickstream. So you just aggregate the stream of events. Yes, please.
So I understand that ClickHouse is very fast for performing real-time queries. Would it be, and it's not appropriate for doing OLTP, like updating, or would it be possible to use it as a data warehouse? For instance, to store data, only append new data, but then perform queries over long periods of time, not in real time. How would it perform
This
in
depends on the kind of your workload. ClickHouse is geared more towards the aggregation.
Yes, aggregations.
So, yes,
When
if you want to do aggregation, it's perfectly suitable. And recently, we got a new feature that allows you to partition your data. Partition was there all along, but now you can move your partitions to some cold storage seamlessly. So this makes it suitable, yes, for aggregating data over a long period of time.
Well, I can tell about the original use case. So the original use case was like similar to Google Analytics. Basically, it's a lot of websites that track their like clicks and see their own reports. But Yandex internal analysts, like there's a service to do this as well. So built like long reports on the whole internet we observe. So like subset of websites that installed Yandex Metrica like tracker. And basically how it's done is like query with lower priority. So there's a bunch of settings that control priority, and we're going to improve it, I think, this year. So basically, you can have real on same cluster queries that go from UI and happen in milliseconds, but on the same time, like someone can come and do ad hoc queries that goes through the whole of it.
okay. This was my question.
Yeah.
Ad hoc queries. Thank you.
Thank you for presentation. I have a question. So we're using ClickHouse for more than 3 years since you released it open source. Thank you very much. And I recognize the big problem really of ClickHouse, not ClickHouse, but documentation. Do you have any plans to improve it? For example, I read changelog. You haven't introduced Amazon S3 integration. How can I use it now?
Yeah,
Not just reading source code.
we are really working on this. The documentation for all features is lacking because we don't have much people who write it, so we only have like one technical writer. But for new features, we try to write them before the merge. So at least for like half a year already, we started to pay more attention specifically to this, and we try to have the documentation, at least in some shape, ready before the feature is merged. So it is prepared for the feature. So I hope it improves. Yes.
And documentation is also open source, and it lives in the same repository as source code. So actually everyone is welcome to contribute.
But the problem is I'm not C++ developer. How can I contribute?
Well, actually you don't have to be, because like oftentimes you can document the feature just by looking at its tests. So if there's like queries that does this, it gives this results. You can kind of understand what the like. If it's domain specific, you can know this domain maybe.
Sounds terrible. We should just try docs.
No, so well, and that's one thing. Other thing is translation. So we actually have support for multiple language of documentation, and besides just writing docs for new features, oftentimes like people find it more convenient to read docs in their native language. It's probably not that like crucial for Europe, but for instance, Asian countries are like full of it, so they like have not so good education of English in schools, and it's also a way to contribute.
And documentation in English became earlier than in Russian even.
Yeah, I think our primary documentation is now.
Well, actually, there was like a period of time that it was written like first Russian then English. It's like around it became open source. So before it became open source, it's a short period after. At some point, like in 2017, we flipped it. So it's English first, then translated to
Now
Russian.
we have like international contributions, so our working language is English.
Yeah.
Docs are primarily in English. Yes, please.
Is there any particular IDE you can use with like MySQL, like Workbench?
IDE, right? So development environment.
Yeah, we
Yeah,
have
the Beaver can do it. IntelliJ products can do it, or like IDEA, C-Line, DataGrape. So basically, any product that supports the DBC can work with it. But there are a few products that can have advanced features for ClickHouse, like syntax highlighting and stuff like this.
So you're primarily using it for time series.
Yes,
All
it's
the examples that you document there are essentially time series.
yeah.
And it is an append-only storage.
Yes, that's right. That's right.
Okay, and what does the motto mean under the your brand?
ClickHouse не тормозит. It can be roughly translated as ClickHouse is fast.
How do you pronounce it?
ClickHouse не тормозит.
Okay.
Не тормозит.
It sounds Greek to me.
It doesn't have breaks. Literal translation.
When you say upset is slow, how slow is it? Because I use it in my production database for Starscale. But now the solution is that I have connected it with MySQL quite robot, and I truncate the tables and I print them all together from start. How I haven't tried to, and I don't know how yet to upset only the new records.
Yeah.
Or by sub-queries or something like
Okay.
is there a way?
I understand your question. So for Upsert, you probably would be better off if you like really need to update. You probably should use a special table engine. So it's not a merge tree engine, but I think it's called collapsing version merge tree engine. So what changes is that you add a version to your records, and on the merges they get overwritten. So this is a way to emulate updates with ClickHouse.
The table does it on its own.
Yeah,
I do
yeah.
inserts, and the table
Yeah.
engine understands that it's
Yes.
in fact an update.
There are some rules how to do it properly, so it's documented. You need to follow it, and
This is actually
Okay, I tried.
one of the very interesting things about ClickHouse. That first you have like a basic merge tree engine that is a merge tree structured append-only engine that merges the parts together. My colleague Alexander will talk in detail about it later. But also you have variations of this engine that like calculate aggregate functions. So you have all this live aggregation result that you can access instantly. Or they can merge the records, like for your case, replace or sum them or whatever. So
Okay.
Thank you for your presentation. So I'm interested especially in the spatial aspect of the ClickHouse, and I was wondering, because now in our use case we use GeoFrames, which is a geospatial library that's connected with Spark, that allows you to make geospatial processing in Spark and store data. So I was wondering whether there are integrations of ClickHouse with geospatial libraries or probably with Spark.
I'm not sure about geospatial integration. So honestly, the geospatial support is pretty basic in ClickHouse. So you only have some, you only have some basic functions, and we are working now to improve this by providing like geospatial dictionaries so that you can test for point and polygon fast, this kind of thing. And also there is some work on providing Z-order indexes. This kind of thing. I'm not sure about integrations with Spark.
I can add that there is an open source library for geospatial data from Uber. It's called Ash3. It's kind of not conventional. It uses like hexagon grid or something. But there's a bunch of pull requests that basically proxy it through ClickHouse. I haven't really heard much about like its usage in like real life. So it's like happened like I think late last year. So it was merged. So it's like just recently get stable. But it seems that they implement all functions that were in the original library. And if you're interested in such kind of queries, you can check it out. Maybe it will work.
Спасибо.
I'm Athanasius. I've made quite an unusual case for ClickHouse. It's a hypergraph database, and basically I'm playing a lot with indexes. And what I wanted to ask you basically is whether there could be an option of automating the primary key index of ClickHouse.
You mean
Something like you know a standard row number thing that ID that
Like
relational
auto-
databases have, you know, automatic.
sequence, right?
Yes,
Sequence kind.
like that. I'm not specifically sequencing, but
Well,
the idea is automating the primary key index and to make it a bit more. What's
yeah,
the
I
advantage of changing the primary key index according to the use case? So it's a bit technical.
So the idea about ClickHouse is that the primary key is not unique. It doesn't have unique constraints. So what it's used for is to read less data. So if you know that your queries are going to hit only these users, or only single user, for example, or like single campaign, whatever, you make an index over this. So your data is yeah. Okay, so Ivan is telling me that we don't have enough time, and Alexander will talk about
Oh, sure. Okay.
this as
No
well,
problem.
so we'll go in depth.
Yes. Yes.
I
Absolutely.
just wanted to say that probably if you want to have a synthetic primary key, it's not useful in ClickHouse because you can't, you don't have referential constraint, and you can just go with empty primary key. It is also possible, so your data doesn't have. So.
Yes, I was not talking about synthetic basically. I'm just. But it's all right. Okay.
Okay, final question. Is it possible to use ClickHouse for machine learning purposes? So are there any algorithms for machine learning?
Machine learning. Yes, we have some integration with. I think Nikolai has a talk about this. We have integration.
I had not today, but yeah, you can
Yeah,
find it in
he
YouTube
did.
in our channel. Actually,
Just
we have
open
all our
YouTube and
talks,
type
so-
ClickHouse machine learning. There's a talk about
Nikolai,
it.
can you
have
talk
basic support.
briefly?
But actually, you can basically you can apply models from some systems like ClickBoost and some basic stuff for linear regression. It's also support.
Thank you very much.
Okay, any more questions?
Yeah, thanks. We use primarily timestamp data for million records per week for hospitals and clinics. We use geospatial MongoDB queries. We go back to the drivers maybe, so something you guys are working on because there is JSON support for input.
Yes, there is a JSON support. Like several kinds of JSON are supported. So you can, where is it? I don't think I have it in my slides, but yes, you can just pipe JSON into insert queries,
Yeah.
and it's going to work.
Analyze and then get it back.
Yeah, then you can insert it.
That's a model you guys recommend.
And also, we have functions for working with JSON strings. So you can also parse them in raw form.
Okay, great. Thanks.
And also we have direct integration with MongoDB.
That's even better.
To be able to implement replication among MySQL and ClickHouse. Do you recommend this?
Personally, I never seen such a
There are third-party
configuration
tools.
replication help.
Yeah, there are third-party tools that implement this. I heard people that use them, and it's kind of okay, but like there are not many of them, frankly speaking. So there are like people that interested in making this better. Probably it will be in like near future. But there are tools. It's called like ClickHouse, MySQL Reader or something.
Yes, that's one.
It's
Yeah.
a set of Python scripts.
By the way, do we have anyone here who contributed to ClickHouse? I think Athanasius, you.
Well,
did
there's several
something.
questions and feedback of problems, some bugs I found,
Ah.
yeah.
So
On
you
the source
sent us
code.
some pull requests, right?
Yes, yes.
Oh,
yeah.
great. We have a special kind of stickers that award only to people who successfully merged the pull requests into ClickHouse. So I am going to reward it to you now. Thank you very much for your contribution. Please send us pull requests. Send us pull requests so that you also can get these stickers.
Hello everybody, my name is Alexander and I'm software engineer at ClickHouse team in Yandex. And today I'm going to tell you about interesting and I think the most important part of ClickHouse, its storage system. As any major database, ClickHouse has a lot of storages. First of all, you can easily process data with very powerful ClickHouse dialect, which even doesn't store in ClickHouse. And Alexander already showed you a few examples of ClickHouse local, but of course you can process external data with ClickHouse server. For example, ClickHouse server is able to read data from files in some format, from distributed file systems, from distributed file systems, and even from other databases like MySQL and MongoDB. But of course, the most interesting is internal table engines. We have few quite simple engines, like engine memory, which allows you to store some data until server restarts, or log, or stripe log. All these engines supports full powerful ClickHouse dialect, but they are not designed for a big data. If you want to use ClickHouse at 100%, you have to use Merge3 table engines family. And is there anybody who already used ClickHouse in production and use Merge3 tables?
Explain merge tables first.
Okay. Okay. We are talking about storage, and first of all, we need some motivation. Why Merge3 engine is very powerful and very nice. It has a lot of advantages. First of all, Merge3 allows you to execute queries in true analytical fashion. They execute it as fast as possible and utilize all available resources. Also, operations with Merge3 are atomic, like inserts. This storage support primary and secondary indices, and even data modification. And it may not sound surprisingly if you previously used MySQL or Postgres, and data modification in these storages is a very common thing. But for analytical storages, it is a quite of advanced feature, and I'll say more about modification in the end of my presentation. And of course, the most operation with Merge3 don't block each other. You can execute them concurrently. And of course, the storage has some features or properties, and at first glance, they may look like drawbacks. First of all, as Alexander already said, infrequent inserts are required. So it is a good point to start to have one insert per second. And I think that this is drawback, actually. And we're already working on it. And I think this year, you will be able to insert data into ClickHouse as frequent as you want. But for now, you should to control your rate of inserts. And also, in Merge3, they have some background operations on records with the same keys. And as Alexander also said, it is absolutely okay for this storage. Primary key in Merge3 is not unique. Okay, and now we are talking about storage, and let's store some data in our storage. First of all, let's create a table. And our table will have a very bad name, it will be called empty, and we'll have just 4 columns. And actually, semantic of these columns is not very important, but before ClickHouse, I have worked in Yandex banner system, and we will use subset of columns from Yandex banner system. The first one will be event date, when some event in our banner system happened. The next one is advertiser ID, who ordered some ads in our banner system. The next one is banner ID, obviously. And the last one is amount of goals which user achieved after he clicked banner. For example, buy some things on website and so on. We will use vanilla merge tree at this moment. Alexander already said that we have several merge tree engines, several variations, and I'll say more about them. But now, for example, we will use vanilla merge tree. Also, we will specify partition expression, and we will partition our table by month, and I'll say more about partitions later. And our table will have a quite simple primary key, just a tuple of order ID and banner ID, just tuple of 2 fields. Okay, we created our table, now let's fill some data. I'll use fake data, and I'll use special table function called numbers, which allows you to read data, to read sequential numbers from 0 to 1 billion in this case. And also I'll use fixed dates. And what is important actually here, that our orders in our table starts from 0 and ends at 1 billion. We have sequential order IDs. And our banners start at 10,000 and ends at 1 billion and 10,000. And we will perform several inserts and repeat this twice, and in common we will have 4 inserts. Okay, now let's look what we have on disk after we inserted our data and understand how merge tree store its data. First of all, let's look at metadata. And for our table, we will have just 1 file. All files in ClickHouse stored on a single path. By default, this path is var_lib ClickHouse, but you can configure it in servers config. And we didn't specify any database for our table, so it will be stored in default database and corresponding default directory. And it is just 1 file, and it contains our create expression. And actually, it is not interesting at all. Let's look at our data, which is much more interesting. All data stored in data directory. As before, we have default database and directory called as our table. And what we will see? We will see a lot of other directories and a file. File is quite simple. It is just format version of our merge tree. And previously we have 1 kind of merge tree. Now we have a more fresh version. It is not important. What is really important, these funny directories with numbers in its name and lower dashes, they are called parts. And part is a central concept of the merge tree. And today I'll say a lot about parts. And if you understand how merge tree work with its parts, you will use this engine as effective as possible. Also, we have a directory with detached parts. It is not important. Okay, as I said before, parts is a central concept. But what part actually is? Part is a directory which contains some portion of data in a primary key order. Each part contains interval of inserts in our table, and of course we have at least 1, and we create a new part for each insert. And these directories and these parts have a very nice property. They can be changed, they absolutely immutable. It allows you to write much simpler code in most cases. Okay, but why we need them? Why we need these parts? First of all, we want to execute our queries as fast as possible and in true analytical fashion, utilizing all allowed resources. So, to execute them faster, we need our data to be ordered in a primary key order, and in our case, order ID, banner ID. But of course, nobody will insert data in our table in our primary key order. Our data will came in the order of time, by even date in our case. And of course, ClickHouse store a lot of data in its tables, terabytes of data, so we cannot allow us to resort everything at each insert. It is very expensive. So we use the most simple solution first, which comes to mind. Let's store our data in a set of ordered parts. Okay, let's look at these pictures, how it works. On the y-axis we have primary key growth, so our data is ordered in a primary key order in our parts. And on the x-axis we have inserts number. And each part contains some number of inserts, and the last insert in our table has n number. So we have some parts on disk, they are already ordered, and at some moment we decide that we want to insert a new batch of data, so we will create a new part. And of course, this part is not ordered in our primary key order, but this data is quite small. It is just a one batch. We can easily sort it in memory, and after that, we can write this data on disk in the sorted order. And this how can merge tree works, how can it writes data on disk. And I think you already guessed that atomicity, if we use such approach for inserts, is very simple. So if somebody has poor network connection, it tries to insert data but can't write complete part, we can just remove whole directory with this unfinished part and continue to work as before, because new inserts doesn't modify previous data. Okay, this is how we can store data in our merge tree. Now let's try to read some data with which much more trickier. Okay, for this purpose we have to look inside parts. So they all have equal structure, so we can choose any. And I choose this one. First of all, we will see that we have a lot of files in each part. We have a file for primary key, which store information about our primary key data. We have files with columns, and now you can be sure that ClickHouse is truly analytical storage. We have not one but two files for each column, so our database is completely column oriented. Okay, and also we have file with information about partitions, and actually we have a lot of other files, but they are not important for general understanding of merge tree concept. Okay, first file is index, and primary index is ClickHouse, I think the only row-oriented file. We just store data of our primary key and store it by rows. So in our case, our key consists of order ID and banner ID, so we just record in this file order ID and banner ID row by row. But what is important? As Alexander said before, index in ClickHouse is sparse. What does it mean? By default, we store not each row in our index, but each 8192th row. Of course, you can change this value, tuning index granularity setting, but by default, it works like this. So, as you remember, in our table, the first order have number 0, because they are sequential numbers from 0 to 1 billion, and the next one is 1, and so on. But in our index, in the second row, we will have order ID number 8192, which means that we skipped all rows between these two numbers, and this is why our index is sparse. What does it mean? So it allows our index to be very compact. We can operate with it very efficiently. We can load it completely in memory when table startups, and even in uncompressed format. Okay, let's look at columns files. The first one is column.bin file, and this file is also quite simple. By default, ClickHouse compresses its columns, and by default it uses LZ4 algorithm. And I think Nikolai in the next report will say more about compression in ClickHouse. But by default, we use just LZ4 algorithm. And what is important here is that for each block, what is important? That we don't compress our column as a single file, but we compress it by blocks. So in our case, we have several blocks in our column, and we write additionally checksums for each block. So if ClickHouse is able to read your data from your columns, you can be completely sure that your data is not corrupted, because we have checksums not only for whole column files, but also for compressed blocks in our columns. It is a very good property. And of course, if you uncompress this block with LZ4 algorithm, you will see just your data stored in this block. And for order ID, you will see these numbers. Okay, but now we have a problem, actually. We have sparse index, which contains just values of our primary key, and we have our columns, which compressed block by block, which stacks one on each on other. So how we can match our index with our columns? It is not obvious. But that's why we have two files for each column, not only one. And solution is quite simple. Let's just, for each column, store a pointer from corresponding index row to offset in our compressed file into uncompressed blocks. We will have these records, these pointers for each index record, and we store these pointers in column name.mrk file, and we call them marks. And I think it is easier to understand this picture. As I said before, we have marks. This is just two numbers. The first one points to offset in our compressed column file, and the next one points to the offset in our uncompressed block. So what is important about marks is that between each two marks we have exactly granularity rows. So as between two index rows we have by default 8192, and between each marks we have 8192. Quite simple. But now let's try to put it all together and write data from disk like ClickHouse does it. So first of all, we have some query with some where expression, and we have to determine which index rows we need to read and or which marks we have to read. It is equal in this case. And it is quite complex task. And in ClickHouse we have a separate model called key condition for this purpose. And today we will use it as a black box. So we will just ask key condition, give us marks, give us index rows, and it will work. After that, when we decide which index rows we need to read, we can found corresponding marks, they match 1 to 1. And after that, we have quite tricky part, because we want to execute query in analytical fashion. We want to utilize all available resources, so we have to distribute portions of our data between all available threads. And the unit of our distribution is called granule. Granule is just a stripe of marks between all required columns. I'll show this on the next picture. And after that, after we have distributed our data, we can just read this data and do it concurrently. And also, if we didn't distribute our data evenly, threads can help each other and steal tasks. So query will be executed much faster. Okay, prepare for the next slide. And it is. So we have our primary.idx file as before. We have our columns with their corresponding marks, and we have a query. And what is important in this query is its where part. We want to read some data from our table where order ID between 6123 and 17,345. We will use key condition as a black box, and it is the first stage of our algorithm. We will just ask, tell us which index rows we need. And it will work, and obviously we need just first 3 rows of our table, so we have to read first 3 granules. And imagine that we have a very slow machine with just 2 cores and 2 available threads, the blue one and the orange one. So because we have just 3 granules, the first one goes to blue thread. Granule is this stripe, so in this case we have 3 granules. The first one goes to blue thread, the second one goes to orange thread, and we have just 2 threads. The last one goes to blue thread again. And at some point they begin to read data, and they read, and they read, and they read. And at some moment you may notice that our orange thread not only have less data to read, it has just 1 granule when blue have 2. But also it performs better. Kernel loves orange color more and gives more processor time for this thread. So at some moment this thread will completely finish, but the first one, blue thread, will continue to read its first granule. So orange thread may decide to help its friend and steal its part of work, last granule, and they continue to read data concurrently. And thus merge tree reads data at load level. And this is one of reasons why ClickHouse is blazingly fast. It utilizes all available resources. Okay, but it was a tricky part. Let's go to the more simpler, but not less important part. And let's talk a bit about compaction. As you remember, in each part we had a lot of files. In our test table, we have 14 files for each part. But if I log in into production server of Yandex Metrica and look into one of production tables part, for example, visit table visits v2, we will see that we have more than 1,000 and a half files for each part. And of course, if we will continue to create a new part for each insert and never remove them, our file system will give up. It is not possible, we will have a lot of files. Okay, but you may already guess why merge tree have merge prefix. And we have a very simple solution for this problem. We have a set of ordered parts in our table, and at some moment we may decide that this is too much. So we can run a background process called merge, and this is just a merge stage of merge sort algorithm. So we have ordered, let's say, arrays of data. We just can read it in the and we do it very efficiently, and this is how it works. By timer at the background merge operation runs, and it just decides to merge some set of parts. It reads their data and store a new bigger part which contain all previous inserts. And what is important that source parts, they are not removed immediately. They goes into background and you can see it on the picture. Merges have some properties. Of course, each part can participate in one successful merge. Otherwise, we will duplicate data of this part. Also, source parts, as I said before, they became inactive. They don't removed immediately. They removed after some timeout. And also, and Alexander in previous talk mentioned about it and was asked about it, we have some additional logic during merge. And that's why they have a merge tree tables engine family. So, if you want to perform some additional operations during merge, for example, you want to have just one record with single primary key value, not multiple. So you can use, in this case, replacing merge tree, which during merge will eliminate the rows with equal values of primary key, and only one record will rest. Also, we have a summing merge tree, which sums values of records with equal primary keys. And for more complex logic, you can use collapsing or version collapsing merge tree, which fold rows with not only equal primary key values, but we have additional column for the storage, this column called sign, and rows with negative sign, fold with rows with positive sign. Also, it is a very nice feature. ClickHouse allows you to store aggregate function states in your table, so you can have a pre-aggregated data actually. And if you need such advanced functionality, aggregating merge tree is your friend. And also, maybe someone heard about Graphite monitoring system. We have a variation of merge tree table engine which rollups its data in a Graphite fashion. You can read more about this engine in our documentation, about these engines in our documentation. But now I want you to remember that the only difference between them is what they do during merge operations. So you cannot have more strict guarantees, just what they do during merge. Okay, also in the beginning I said that merge tree allows you to modify data. And how it works? It's time for partitions. In our table we had partition expression, and what does it mean? We partitioned our table by month. So partitions in merge tree is just the logical entities. They don't stored on disk. You allow it to have any partition expression, but by default, a lot of users use monthly partitions. And these partitions allows you easily manipulate this data. They don't affect query performance. They at least they make it worse, but they cannot make it better. And they allows you to actually to modify your data. First of all, you can easily remove a lot of parts which correspond to one partition from your table with alter table drop partition query. And as maybe you remember that in our table I just used 2 dates from October 2018 and from September, and for example I can remove whole partition from October, right? Remove October from my table. And also I can temporarily remove this data with detach query, alter table detach, and return it back with attach query. Okay, but sometimes partitioning is not flexible enough. And for this purpose, we have mutations. What is mutation? Mutation allows you, we have two variants of mutations. The first one allows you to remove records from table, which satisfy some predicate. The next one allows you to update values in columns, which also satisfy some predicate. But what is important, they are not designed for frequent usage. They have nothing common with MySQL's delete or update query. They are very similar to merges. Each mutation override all touch data on disk. They work in the background, and again, as in merges, original parts became inactive. Let's look how it works. For example, we have a set of parts and we want to delete some rows from our table. And mutations, after you executed alter table delete query mutation, background process begins to read parts one by one. So it reads the first part, removes data, source part goes to background, became inactive. After that it reads the next part, and so on. That's how mutations work, and that's why they are not designed for frequent usage. You shouldn't run 1000 mutations per second, nothing good will happen. You will kill your disk and you will consume a lot of CPU. This is a bad idea. Actually, they have some optimizations, so they stacked into one expression when you execute mutation, but frequent mutations is not a good idea anyway. Okay, now let's put it all together. Imagine that we have a table with just 5 parts. 3 of them are active, 2 of them are not active. At some moment, select query begins to read data, and it reads data only from active parts. At some moment, some inserts may happen, but they don't affect select queries. They continue to work concurrently, they just add new active parts. And at some moment, we may decide to remove all outdated parts. After that, some merges may happen, and they'll replace our parts with a new one big part. But what is important here is that select continues to read data from old, outdated parts now. And even if at some moment we will decide to remove, start cleanup and remove old parts, select continue to read its data, and what is important is that parts that somebody used will be never removed. They have some kind of ref count value. So when select finishes, we can remove these parts, nobody uses them, they are inactive for too long time, and that's how merge tree works. Something may happen after that. Okay, let's summarize. Who knows what is it? No. Yes, it is Matryoshka. It is a Russian folk toy, and the main idea of this toy is that you can put smaller one into bigger one, and so on. So merge tree, it has the smallest meaningful unit, and it's called block, and it is stored compressed. Blocks stacked into columns, columns organized in parts, and the set of parts may be logically divided into partitions. That's why this Matryoshka is slightly transparent, because this is logical entities, it is not stored on disk. And the set of all partitions is our table. And this is how what merge tree consists of. Okay, and some things to remember. At this time you have to control rate of your inserts. You should have one insert per second, it is a good amount. Also, merge tree have background merges, and even when you don't run queries, even if you don't insert data, ClickHouse can still consume some disk I/O, some CPU, and this is how it works. Also, we have some additional fault logic in merges, and that's why we have a family of merge tree table engines. Index in merge tree is sparse. You can change sparsity value with index granularity settings, but I don't recommend you to do it if you don't completely sure that you need it. So, because index must fit into memory and default values are good enough. Of course, index determines order of data on disk. And what I didn't said before, that use of index is always beneficial. Even if your query touches a part of your index, or use, for example, some monotonic function of your index, it will be executed not slower than full scan. So use index, indexes in ClickHouse are awesome. And if you want to perform some modifications of your data, you can use partitions. Partitions cannot improve your cannot speed up your selects, so don't try to create a lot of very small partition your data by second. It doesn't make sense. And they allow you to manipulate this data easily. And if partitions is not enough, you can use mutations, which are also not designed for very frequent usage. Okay, that's all. Answer your questions.
Amazing fast.
Не тормози. Okay.
Why do you say that partition
They cannot speed up your queries. You ask why?
Yeah.
Oh, because we don't use information about partitions. We store information about our index in each part. So we can easily understand that if when we execute query, that we don't need to read data from this part at all and remove it from query. So partitions, they can improve slightly performance. They would be able to improve performance, but they don't. If you, for example, read data from 1 month and you can remove all other months. But for example, we have all this information in our parts and it works fast enough.
Yes, but in cases you write data to not to one partition only, you have one directory, just one directory.
No. Partitions is not directories. They don't store on disk. We store parts on disk. Partitions consist of parts. So.
What I confused by the first image we saw about the
Matryoshkas?
the first image with the directories of one.
One part. Maybe I said partition, but I was not correct at this moment. So, okay.
Can I try to explain? Partition is a feature that like prohibits mergers. So basically it says ClickHouse never merge rows into a single file that have different values of this expression. So, for example, it could be month. So never put like rows of different month into the same files. So it's like a logical thing. So it's like your way to control how to like manipulate your data. So it's the primary use case. Otherwise, you could just put like date in the beginning of your primary key, and your filters on dates will work fast.
Okay. But here the partition is month.
Yes, in this case, partition is month.
Okay, so it's part of the directory.
Yes, partition is a part of directory's name. Actually, I didn't show it on the slide, but parts directory's name has semantics. The first number is its partition number, actually. We have, in my example, we have October, so it is 2018 October. The next one number is the first insert number, which each part contains. So the second number is the rightmost part, which each insert contains. And the last number, in this case it is 1, is how many merges happened with this part. So parts with number in parts where we have number 0 at this place, it is just freshly inserted parts. They contain just one block, just one insert number. And this concrete part was merged and contained 1, 2, 3, 4 inserts.
Okay, talk about one set with 1 million rows.
Yes.
Okay.
If your inserts has more than 1 billion rows, then they will be divided into several parts. Yes. And in this sense, inserts may slightly be not atomical, but
There is a setting to control it.
yeah, you have a settings to
You will
control.
create 1,000 directories.
No, if you have 1 billion,
1 million records with different partition numbers.
Yes, in this case you will have a lot of parts. But
one bus will be 1 million directories.
yes, but in this case we also have a limitation. We have special settings that don't allow you to insert 1 million directories on disk. By default, one insert can have, I think, 100. You can touch 100 partition. And in another case, you will have an exception. But you can tune the settings, but I think something went wrong with your partition key.
I just mentioned the difference and why it is used.
Yes.
It means it's a directory.
Yes.
What happens if we have a distributed environment with regard to replication and high availability? Do you copy files to multiple machines?
No. In merge tree, and I didn't cover it in my report. We have in ClickHouse different ways to distribute your data, and for each of these merge tree variations, we have replicated prefix, which implements replication state machine, which allows you to reliably use merge tree on different servers and have different replicas. So, for example, in this table, which I showed you in production of Yandex Metrica, use a replicated version collapsing merge tree engine, and they have 2 replicas in each shard, and also merge tree supports sharding, and we use different mechanism for sharding. It is called distributed table. This table don't store data, it just allows you to execute your query concurrently on different shards. And you can read more in our documentation, you can see some presentations on our channels. We have a lot of speeches.
So all the presentation that you forward is primarily in case we have installed ClickHouse on one single machine.
Yes.
When we have multiple machines, something you do some more sophisticated stuff to replicate data so that.
Yes, that's why Alexander said that if you need replication, you need Zookeeper. Replication use Zookeeper and store metadata. So we don't try to implement distributed consensus by ourselves. We use Zookeeper, but this mechanism is very reliable. It is used for many years in Yandex Metrica, and I think they didn't lose data. Okay.
So 2 months ago, the guys here organized a very interesting presentation showcasing Apache Druid. So the problems there in Apache Druid is I think the same more or less to have real-time analytics in timestamp data.
Yes.
So I was wondering whether there is a benchmark or something with comparing the 2 systems. So which are the differences? They use pre-aggregations. My understanding, you do not use pre-aggregation, so.
Yes, it is a recommended way to store raw data and aggregate it on
So
disk.
I was wondering if there is something that compares, how to compare the 2 systems or something.
I don't know about benchmarks. I've read a very interesting write-up comparing ClickHouse, Druid, and Pino from one of the committers. I don't remember. Maybe he works on Pino or Druid. It's very interesting to read, and the basic conclusion is that benchmarks won't make much sense here, and you have to evaluate for your use case, because architecturally the systems are similar. What people who are familiar with ClickHouse and Druid often cite as an advantage of ClickHouse is that it's much simpler to get started, to configure, because only one kind of node, you can start small, etc.
I won't write you off. That's why how you can use ClickHouse in distributed environment, so you can have different shards, and each shard you create replicated merge tree table, which transfer data between nodes of one shard. And if you want to execute query, to speed up your query and execute it on all available machines, you just enter into distributed table, select data, and this select will be executed on each shard and will be aggregated into one on the initiator shard. That's how it works, but it is a presentation of my former colleague, and I'm not sure I can give you another talk today. Okay.
Another question. Thank you for the presentation. It was very very easy to understand.
Thank you.
How do you turn the columns into rows? If you can explain briefly, this how this is taking place in ClickHouse, and especially how memory is allocated, how much memory is allocated for doing such a thing. I mean, from turning the columns into rows so that they're presented at the final table.
I can very briefly to say about it. And as I said before, at low level, our threads read data by randomness. So each thread reads data from all columns. After that, it constructs internal structure. And now we have some refactoring, but previously it called block. It just contains same columns in memory. So in memory, we also allocate data in column-oriented format. And after that, this block, you can read this data by rows, for example, but you have to iterate by columns on disk, in memory. And maybe Nikolai, in
Yeah, I
his
will tell you a little bit,
presentation, will say more about
but the simple answer at ClickHouse do not store data in rows because it is truly column oriented. So when we process data in memory, it's also in columns, while in smart parts. We convert data into rows only on the final stage when we want to send data to user. Then we do it. But
Yes.
all processing is columnar.
Yes, at the point you send the data to the user. That's what I was asking. How much memory is allocated for turning this into?
Well, about memory, it is maybe difficult to say because every column may kind of spend some amount of memory, which is usually more that you think, but well, it is a constant amount of memory, but it could be a little bit bigger than actually you expect from single row, because we process it by blocks and because we have some like extra buffers to make it faster.
Okay. Right. Thank you.
Okay.
Thank you.
I think no more questions. Thank you.
So well, let's continue. My name is Nikolai, and today I will tell you about data processing in ClickHouse. Actually, this presentation could have been called why ClickHouse is not slow, why it is not не тормозит. But actually, there is no one silver bullet. There are a lot of reasons, and it would not be enough to make a whole presentation about everything. So it is data processing. And I have chosen just a few topics. I will tell about data layout and compression, how data is compressed in disk, in memory layout, how data stored in memory in columnar format, about pipelining and parallelism, how do we use our CPUs to make query as fast as possible, and about specialized data structures. So let's start with the first part. It's about data layout and compression. And as Alexander said, ClickHouse column-oriented database, and it stores data in columnar format in disk and in memory as well. And when you execute query, it really needs to read not the whole data, but only few columns used in this query. And it uses different kind of indexes, like primary index or maybe secondary one. So we need only to read some parts of files. And very important thing that these files are compressed. And in ClickHouse, you actually can select a compression method for every column in table. It works for merge tree, and you can see in the example on slide that I have created very simple table with name codec example, and it stores a column with date time. But this column stores same data with different compression methods. The first one is default, it's LZ4. Next one is a column without compression, just raw data. Another one, LZ4 variant with high compression rate. that is study. And the last one, maybe the most interesting, it's compression codex chain. So we use double delta and LZ4. It means that we apply two different methods one by one. And later I will tell why this can be needed. Actually, I have found a pretty beautiful compression page on GitHub page, which shows you why do we need different compression algorithms. And this picture shows difference between compression ratio and decompression speed. The most important things for ClickHouse. It shows it for Wikipedia database. It's first 100 billion bytes of Wikipedia and for specified CPU type. And usually when we choose compression methods, it's some kind of balance between speed and quality. And some methods are better, but in general we can say which one is better, and we need to specify it for column, for each column. And actually, if you open this page, you will see that it contains not the single one graph, but you can choose between different type of CPU and different type of datasets. So if you think that broadly is the best for Wikipedia, it may not be true for numeric data, for example. So let's compare our different compression codecs. And actually, I have inserted some data from Yandex Metrica table. It's real-time steps. And when you insert data, you can actually read from ClickHouse table, system parts columns, how many bytes it takes. Generally, it has two different two indented columns. It's compression, compressed bytes, and uncompressed bytes. So we can divide the first one by the second and find out how well our data is compressed. So for non-compression, it's almost 1. For LZ4, it's the same, and it is compressed 22 times. For the TSTD, it's compressed better, almost 63 times. And the best one is double delta with LZ4. So I was so glad that I liked to show you how this double delta works. Actually. And let's imagine that we have some data from sensors. Like you have sensor which sends data about every 40 seconds. But maybe not exactly 40, sometimes 38, sometimes 42, and so on. Basically, you will have data like in the picture, it will be slowly growing up. And this data, in that way, is not very good compressed, because generally we have different numbers, different bytes. And easy thing we can do, we can calculate delta transformation. Delta is just the difference between current row and previous one. So our graph will look like that. Now we have time deltas, and they are not very different, like between 35 and 45. And now it's compressed well. If you use any compression method, it will notice that, okay, we have a lot of similar numbers, so we can do good things to compress it. But it's not all what can we do. First of all, we can apply our delta transformation again. And we will have a graph like this. Now, not a lot of things have changed, but we have time deltas which are close to 0, actually. But if we know that our numbers are close to 0, we can do nice thing. We can apply various lengths encoding. What it is? It shows that we can encode 0 with single bit. If we have very small numbers, like between -63 and 64, we can use 8 bits, and more bits if our numbers are big. So if we apply this information, we already compress data pretty well. And it is what double delta does in ClickHouse. That single one codec. But we still can do better. We can apply LZ4 up to it. And I would like to ask if anyone can guess why. Nobody knows? Okay, actually, I can try to explain. Okay, let's imagine that your sensor is very good. Like, it almost insert data every 40 seconds. Then, even if you compress with double data, you will have a lot of 0 bits. And in this case, it still can be compressed because you will have 0 bytes, and therefore make it better. Just simple reason. Let's go on and let's compare read speed. What I do, I just read this column and measure how fast it is. Actually, you can do it again inside ClickHouse by using its own tools. We have a system query log table. Does anybody know what it is? Okay, some who use ClickHouse know about it, and it's a really great tool. And usually, if you use ClickHouse, you should enable. It just contains all executed queries and some metrics for them. Like, it's easy, you can go to documentation, add special setting in the config, and enable log queries equals 1. And when I measure speed performance, I also drop file system cache, because I want to measure how long does it take in real life. And it's usually what should you do. And where we compare speed, like, okay, from system query log you can read how fast was your query, and by query ID you can find some useful metrics. They are written in profile events columns, and you need to use special feature from ClickHouse which named array_join. But I will need only 2 metrics. It's real-time microseconds and discrete microseconds. It's actually time for all threads used for this query. And if we get these numbers and divide again discrete by real time, we'll understand how long did it take for query to read from disk. Well, and for this query, we see that for different compression codec, it's different numbers. If we do not compress, we spend like 87% of query while reading from disk. If we use ZSTD, then less than about 30%. And better compression we have. Less time we spend reading from disk, and faster query is. And this is usually true if you have I/O bound query. Like if your bottleneck is I/O, then compression will help you. You may ask, what if my query use CPU mostly? And I will show you this slide, which uses another one query with hash functions. It's also actually not very heavy. But if we compare disk read ratio, it already will be about 5 to 3% of our query length. So it is not significant right now. If your query is CPU bound, then compression did not take a lot of time. But if you do not use compression, your query still will be slow because it could be still I/O bound. So it's actually pure win for ClickHouse. Well, now let's go to the second part, and I will describe you how data is represented into memory. Again, some revision. ClickHouse processes data by blocks. It's structured in memory, and the block usually contains several slices of columns. We cannot store the whole column in memory because it's huge, but in this slice we can have like thousands of rows in total. And each column usually represented as several consequences buffers. And it is easy to understand for integers. It's just an usual array, but with tiny features. For example, we have special -1 index, which contains 0, and it helps to avoid a lot of branches in code sometimes. And we have special 15 bytes padding at the end, which is helpful when we want to use some sync instructions. When we store strings, it's a little bit more complicated. We already have 2 buffers. One buffer for characters and another one for offsets. So if you want to store 2 rows, ClickHouse. In data buffer it will be like click/0 house/0. And in offsets is written, it's actually prefix sum for our string lengths. But it's easy to understand that offset points to the beginning of next row. So offsets by index -1 points to click, offset by value 6 points to house, and the last one points to our padding. And it's pretty comfortable to use such structure because easy to use in instructions actually. And arrays stored in the similar way. If string is an array of chars, then array it is an array of something, like integers. So the idea is the same, but there is difference when we store array on disk. Like strings are stored in single file, but arrays in 2 different. And actually, I have more difficult slide with multiple dimensional arrays. Well, and actually it doesn't bring any information. Basically, n-dimensional array, it is just an array of n-1 dimensional arrays. And it has several levels of offsets, and offsets of next level, the second level, it points to offsets of previous level. Well, if it is complicated, I think it can be. What you need to do is just to look at this picture, think a little bit, and you will get it. But I'll move further. Now I have described how our data is stored into memory, but right now I want to tell how it is processed. And I would like to describe ClickHouse functions. They have several features. The first one, it's about purity, so our functions are pure. It means that they are depend only on arguments and not on everything else. And it's very important because our functions execute in multiple threads usually. So functions should be pure, maybe with some exceptions for dictionaries or so on. They are strong and strict typed, actually, and it means that first of all we know function types before we execute query, and it helps us to make a lot of specializations. So for function plus, we will have different code for every pair of arguments. For example, if you sum 8 bytes, 8 bits numbers and 16 bits numbers, result will have, like in this case, 32 bits, and if you sum signed and unsigned, result will be unsigned. And again, ClickHouse functions, they use these slices of columns. It means that every function, every argument of function is actually a buffer, and we process a lot of rows at the same time. And it reduces the number of virtual calls. You don't need to call function on every row, but on this big batch. And it's easy to make synced optimizations. But not very pleasant point that it's complication for UDFs. We actually do not want to have UDFs which will be slow, so we need to do the same interface for user code. It may be a difficulty. So next, I would like to show you an example of one function implementation, actually. And are you ready to read C++ code? A little bit. Are you brave enough?
Show us.
So reading. That's how it looks like. What it is? It's a function which compares two strings. That's all. And says which one is greater. It takes string A with this size, string B which is size, and returns integer, like -1, 0, or 1, like in Java, if it's less, equal, or greater. What's interesting in this function? That it is synced optimized. And I think you can easily understand this loop. It has offset inside, and it's first of all it's 0, and then we increase it by 16. And the most difficult part is those 3 rows, with functions like underscore underscore something. And this is our synced instructions. What we do, we copy 16 bytes of each string in separate registers, then compare 16 bytes at one time and calculate special mask, which says if bytes are equal or not. And if every bytes are equal, we can skip a lot of data at the same time. Well, now I think you need to reason again, because I would like to show you some assembly code. Yeah, I just like it because it is even shorter than C++1. It's the same loop, and I have a comment which explains what it does. Like, again, we have offsets which are stored in one register R8, and at the beginning of loop we increase it by 16. Pretty easy. Then we compare this offset with our string sizes, and if it's greater, then we exit our loop. That's clear. Then we do what I said, we load our data into registers XMM0 and XMM1. We compare 16 bytes in this instruction, and we move our bytes into special bit mask. In gear X, we invert it, and if it is 0, then we continue our loop and go to the first row. So our loop is pretty good optimized. It uses instructions, and sometimes it is very important to look at it because you can be sure that your code is vectorized. Usually it does, but still, we need to check. And why I show you this code? Because of it's funny, but actually because it is pretty simple. Right now, if you look at it, you may say that, come on, what do you do? Probably you read some bytes outside of your memory, because we have size of string A, but we read 16 bytes, and we do not check that we have these 16 bytes in our memory. But it is legal because of this 15 bytes padding we use in our columns. If we use this padding, we don't need to write extra code which checks that our string is short enough, and we need to exit this loop earlier. It's just what you see. It's pretty clear. And sometimes it works better than compiler can, because compiler does not know that we have this 15 bytes buffer, but we do. So that's one of the things I like in ClickHouse, that it's pretty good optimized for simple instructions. So now we can breathe out. It's over. No assembly more. Just pipelining. The third part. What's about pipelining? What's query pipeline? Actually, it's pretty easy. I have a very simple query which calculates average lengths of different URLs from his table. It's just page hits from Yandex.Metrica. It doesn't important. But if you look at this query, it's pretty easy to say what it does. It's pretty easy to separate it into easy steps. Like, first of all, we need to read our data, then we need to calculate our function, like expression, to check if URL is not empty. Then we filter our column, calculate its length, and do aggregation. Those steps are easy, and those steps are separate, so we can do it independently. And this thing in the right part of the slide, it's just some blocks connected with arrows and what I will call pipeline. And actually, pipeline in ClickHouse can be a little bit more difficult. It's not always just a simple chain. It can be any graph directed, but it even can have loops inside. And this graph supports parallel execution, which is also very important to ClickHouse because we want to use all CPU. We want to execute our query as fast as we can. And sometimes it is even dynamically changeable. If you need to add step, and sometimes you do, you can implement it in ClickHouse. And I will show you example. But first of all, about parallelism. You can parallel your query in usually two ways. And the easiest one is parallelism by data. The idea is clear. You have data, and you can split it into different pieces. And to say that every thread has this own copy of pipeline. And it can do it for every part of data independently. The only difference that when we calculate average, we do not calculate it completely. We just calculate sum and count. That's all. Then when we execute it, we can merge data together, union our results, and calculate average finally, like divide sum by count. And in this way it works very good, because division is made in single thread, but it's actually fast operation, especially if you don't have a lot of keys. But sometimes it's not enough. Query can be more difficult. This is an example of difficult query, and why it is difficult, because it has ordered by. It needs sorting, and we can execute the first part of our pipeline in parallel, but it's only 2 steps. Like we read block and we sort it independently, but we need global sorting. So our parts of pipeline needed to be merged together, and after that we have single chain of long hash functions. But actually it's not a problem, because we support vertical parallelism. It means that these parts of pipeline, these 4 blocks, can also be executed in different threads. So we can use up to 4 threads to execute this in parallel too. But sometimes we have even more difficulties for this query with sorting. It performs sorting into memory. And if you have not a lot of memory but a lot of data, your query may say that the number of memory the memory is over, so it will throw exception. But actually ClickHouse can sort our data not only in memory but on disk, and you can enable option max bytes before external sort, and say how many bytes do you have in your memory, how many bytes can you use. And if we enable the setting, when you run out of memory, ClickHouse will do nice thing. It will spill data on disk. And it will create an extra step which buffers the data. It spills data, and now you can continue executing it. You sorted another one part of data, again run out of memory, spill it on disk, and do it several times. After that, when you read all the data, what you need to do, you need to merge data together. Like read data from buffers and execute merge sorting. And your data will again continue to go to this first sort step. And this is how our pipeline dynamically changed, and it even has loops inside. It's a difficult case, but I like it very much. It explains how it can work. And final slide in this part. It shows how real pipeline looks like. It's actually the same query. I do not know if you can see it. It's a little bit more difficult. It has like totals and extremes, but it shows those basic steps of reading, filtering, executing function, aggregating, and so on. And actually, I already say half a year that it will be available inside ClickHouse soon, and sometimes I will do it. So these pictures probably will be available by query.
Excellent.
Nice.
Excellent.
So maybe it will be the next task I do after this meetup. But now come to the last part. It's about data structures. Do we have some time? Yeah, we have 2 minutes. But I will tell only about basic ideas which use ClickHouse, not about data structures in details. And when you solve some task, you actually usually have a lot of questions. Let's take as an example string search. When you say that you want to search one string in another, what can you ask? For example, if you need to do an approximate search or an exact, can you use regex or not? Regex or not? Do you have multiple or single needle? It's what you want to search. Or do you have multiple or single high stacks? It's where you can search. Like, do you have short or long strings? Like, IO strings is UTF encoded or just bytes, or maybe it's words from real language, or maybe they have collation, or maybe you can compare strings not capitalized, a lot of options, and for every option you actually can create a very specified but very fast algorithm. And it's what the ClickHouse does sometimes. If to tell about concepts which use in ClickHouse, first of all, if we have a very good implementation of algorithm, we can use it. We can take it and put it into ClickHouse. A good example is synced JSON. Can you guess what it does? I think it's easy. Yeah, it has two words actually, synced and JSON. So it's a JSON implementation which is pretty fast, really. So we use it. Sometimes we can use algorithms, but not only use, but improve. Next one example is Valnitsky. Well, I don't think that you know which algorithm does, what this algorithm does. If you know, raise your hand. No. But actually it is substring search. And when you say about substring search, yeah, you have in mind a lot of algorithms like Rabin Karp or Knut Morris Pratt, or maybe even you know, binary search. But this case is optimized when you have a single needle, but a lot of haystacks. But actually we improved it. We used use multi-Valnitsky, which is used when you have a fixed number of needles, not infinite, but like small number, and it works faster than if you run a lot of Valnitsky separately. And another one example for memcopy, like you can ask why do not you use memcopy from libc? Because it's slow. First of all, we have Chinese version, which is much faster. And don't be afraid, this Chinese version is good. We didn't have any problems with it. But for some cases, we even have more specialized things, like function memcopy small allow read write overflow 15. And this thing again about those 50 bytes buffers, because sometimes you know that you have enough memory and you can implement it better. Another good example is group by. Well, sometimes you can specialize not only algorithms but data structures. And as Alexander said already, for group by we have 40 different hash tables. I calculated it before Meetup, actually I was wondering how many, and it's exactly 40. And probably I could have told you about how it works, but we don't have time, so let's see. Another points are pretty easy, pretty clear, that when you measure performance for your case, you usually need to do it on real data. Because if you test on some generated data, it usually does not show real performance. You can think that your structure is well optimized, but you will run it on real data. So if you have your data set, take it, not some random generated stuff. And profiling is very useful. I think not only in C++, but on every language. Do it and see what's slow, improve it. So, some slides about group by. Are you ready to listen to it? Well, actually, I will tell you about group by. If you think that it's too much for you, you can just leave. I wouldn't mind. I wouldn't remember you. But, okay, group by use data structure which is named hash table, as I already said, and you probably understand how it works. But ClickHouse is parallel, so you need to do it in many threads. And basically, it is just hash table which stores your group by keys and some values which is suitable for aggregation, but which stores intermediate result. Like for average, it's again sum and count. So in separate threads, we read data and insert it in the hash tables. And we have separate hash tables for each thread. When we did it, we have a special merging phase, when we need to combine our hash tables into one together. And finally, we do our calculation. We divide sum by count and can get result. Well, if you're attentive, you can see that the second phase about merging, each can be done in many threads in this implementation. And it is okay sometimes. if you have countries, for example, you don't have a lot of countries, and when you merge countries together, it's fast enough in single thread. But if you have AP addresses, for example, then it is much slower. And for this case, I have even better picture. Well, it's two-level application. And basically it works in the similar way, but in every thread we have not a single hash table, but 256. And what we do, we take our key, calculate very fast hash function, and divide it by 256. And insert this key into one of these 256 hash tables. We do it in every thread, and when we merge data, we need to merge only data from different buckets, because keys are not intersect together. And now we can do it in parallel, and we even can finalize data in parallel and move it to client. Well, hope it was not very complicated. Again, if you did not understand it, you can meditate on this picture. It's pretty clear. So, I have another one slide which says why we have a lot of specialization for hash tables, but basically it depends on key. For example, if you have key with 8 or 16 bits, you can replace hash table to lookup table, because it is faster, you don't need to calculate hash function result. If you have several keys but fixed, you can connect them into one big number. If you have strings, you can apply multiple optimizations. For example, you can pre-calculate hash of string, and it will allow you to merge tables faster and resize table faster. And we even have something like small string optimization. But let's skip the slides still. I want to go to conclusion. First conclusion, that sometimes you need specialized data structures. If you see that part of your algorithm works slow, then it may change your performance significantly. Then I said you about different ideas from ClickHouse, and I hope that you like something and you will use it in your projects probably, especially for real data sets. Test on them, not on trash. And if you brave enough, if you think that you can contribute to ClickHouse, you are welcome. So thank you for now. And if you have questions.
We talked about earlier about the survey varies in different databases. I would like to ask, based on your experience, both from internal users as well as external users, what is the biggest barrier to entry for those who want to migrate? I'm not talking about those who want to start a fresh system based on a ClickHouse, but I'm talking about those who already use another online analytical processing engine for analytics and want to migrate everything to ClickHouse. What is the biggest difficulty for those people? Based on your experience? If there is any.
Well, actually, I don't have experience because we are not users, we're developers, but
Maybe one knows.
maybe one knows. I can guess that maybe the most difficult piece is to understand how ClickHouse works, because it can be not very convenient when you go from MySQL to ClickHouse. Like, you need to understand that it's analytical databases, that the index is not unique. You need to think how you need to insert data. You cannot insert single rows, but batches, and so on.
Let's assume that we're talking about people who have experience with analytics within their company and they have multiple systems to choose from, right? I'm talking about experience, people who build analytical dashboards on export database. Do you think it's because of the, how are you going to get more traction? It's with more meetups, more videos, better documentation, better marketing. What is the biggest challenge, do you think, to move to this great data?
Let me try to answer that. So how it usually works? So sometimes, like the typical case is like this. So there's one person in the company who's talking about ClickHouse, like on Hacker News, on Meetup, or like on some conference, whatever. He uses something else, like for I don't know, Green Plum, I don't know, Hadoop, something, Spark.
Elastic.
Yeah, so basically he became curious. So people say that it's a cool thing. Let me try it. So he takes backup from his system, like usually some CSV, Parquet, whatever, some file, and he just puts it in ClickHouse. And he takes some queries from his like old system, whatever it was, and try to replicate them to this like subset of data, and try to like take a look how it's like fast, really fast, like in exactly my use case. And oftentimes he kind of gets surprised of results. So like oftentimes we will see like order of magnitude, even if radio solution or commercial. So and after that he just goes to his manager and says, hey, we can drop this commercial thing that costs like $1 million a year or something, in favor of this free tool that like it's the people say that it's scalable, so it won't be limited in the future. So it's like open source, pretty good license, and so on. And that's how it usually grows. So there are other ways to do it, but it's like the most typical one. So,
is there a Dockerized version of ClickHouse?
yeah, there are official Docker. So there's a official Docker image, basically, which is like raw Ubuntu or something with the package on top of it. And there are like independent people who do like integrations with other Docker ecosystems like Kubernetes, Helm, and stuff like this.
In your presentation, as far as I understand, I think there isn't an optimizer for ClickHouse, okay? There is, but so how, especially for joins, how, so you have to make it yourself to understand, you know, the, how it can be optimized, rather than leaving it on to automatically to be.
Yes, right now you need to do it yourself.
Okay.
And actually somebody could say that it's maybe even a good way for analytical database, because ClickHouse does what you like written.
Yes, yes.
It's pretty clear.
Sure.
Sometimes it is good, sometimes it can be optimized and probably we will work in this direction too.
Okay.
There are some optimizations, right? When you move conditions
yes.
to freeware, or when you, it was recently added when you evaluate constant expressions.
Sometimes we do it, yes. For example, we push down predicates for joins, and because it's just clear, if we can do it, it will optimize for sure. But some things are not clear.
So that does it work for distributed as well? The predicates are pushed down for distributed joins, like to the shards, and
yes,
on the aggregate.
They pushed on the client before even you execute join, and then move to service.
Can you please tell about preware? What is the real use cases? Because I read the documentation, but to be honest, I never use preware, only where, because it's like from MySQL background.
Well, actually, it's a nice thing which helps you to read less data.
Where is not making that?
Well, actually, it works automatically. If you create an entry table, some part of your where condition sometimes, or even every time, moves to prepare.
Yeah,
I can say how it works. It's pretty easy. When you have a difficult condition like where x and y, like x and y can be any function. You usually can, for example, calculate the first part of this query, x, and read only columns which are needed for this x. Then filter some data and understand that you can skip some granules. So what you do, you skip those granules and read the other part of columns, like the other half of columns, but not for all the rows we read before, but only this part. Well, I think I didn't help a lot.
So the gist of it is that now it mostly works automatically, right? So
It works automatically, yes.
You move conditions to preware, and this is more like an advanced optimization technique. When you look at your query and see that it's reading too much data, and maybe you can understand that you could manually tell it to read less.
Maybe I should try.
Yeah, try. This is for queries that read too much and that you understand might read less.
For example, for real example, you have like also like from Yandex Metrica hits data table and column URL, and I want to filter like URL contain word by, for example, like filter by. So does I need to move this URL like person by to pre-where, or it can be anywhere?
Well, actually you can do it, but basically heuristics
Makes no
which
sense.
makes sense. But first of all, you need to choose conditions which filter a lot of rows. For example, you have a tiny column, maybe not URL, but URL domain, and you can filter, but this URL domain, and if you know that it filters a lot, then you can move it into preware. And then you can choose these conditions which are easy to execute. And probably URL domain is easy to execute, easier than the whole URL because it's usually short. You can even have a dictionary for it. Like,
For example, if you filter by URL, you could also have filter by like HTML content of the page. For example, if you have it, it's like few orders of magnitude larger column. So, and if you like put this URL condition in the preware, you'll have to fetch content only for those rows that actually there was a match. But if you just fetch URLs, it doesn't make sense because you already read the URLs to filter this. So it's basically a relation to save I/O. When you have like something small and something big.
but actually need to store this domain's column and also separate them.
Not function.
Yeah. Well,
So that strings have 0 bytes at the beginning and at the end, but arrays do not.
actually, arrays actually store. Yes, arrays don't store 0 bytes at the end because it's not just strings. Actually, we store 0 bytes because it's just convenient to use. Some C functions they think that strings need to have /0 at the end, and we do not copy data 2 times with /0. So it's another optimization. Yeah.
Related question. So the picture you saw about the data structures for integers and strings and so on are in memory, right?
Yes, mainly.
Is the same format, like how does serialization work? Because you said sometimes you need to store it on disk.
Yes. Yes.
Is it the same or like use different?
Actually, it is the, how can I say it? We just have special formats which allows you to serialize rows, and basically it is done in the same way as in merge tree. But we do not use indexes, but we write columns in the same format. It is column oriented, and it is the fastest thing you can do in ClickHouse. Well.
Are you aware of Apache Arrow? That's or there are technologies that try to have the same format, so it's like 0 copy. Like they don't.
Yes, we just use in ClickHouse native format, which is 0 copy for ClickHouse.
Okay.
Because our data is stored in different ways. So. Yeah, please.
Is it possible to optimize further the database by using either classes or any views? Are these features supported in cloud?
Yes, it is possible, especially it is possible if you use materialized views. Like it is probably special ClickHouse feature, maybe not very special for ClickHouse, but it allows you to calculate aggregate functions beforehand. Like if you have a set of queries you will ask, and you know that it has heavy group bys, you can do group bys before you execute this query. And in some cases it can optimize it very well. But basically, I think you need to read documentation about materialized views. It's more clear.
Do they have any impact? I mean, in order to implement materialized views, I assume that you also have to implement some extra write somehow, somewhere. So
Yes.
does this have any impact, any side effects, or any effects actually?
Actually, I must say that it works like trigger on insert. So you create materialized view to some table, and when you insert data into this table, it is also inserted into materialized view at the same time, but sometimes aggregated, like some of those. And like you store more data a little bit, but when you query this view, it works faster. It reads less data. Yes.
Material are automatically populated on new inserts too. Is this true?
Can you ask this again?
Okay.
Use populate.
Let's say I create a material.
Yes.
Yes. And I insert new data.
Yes.
If I insert new data on the underlying table, are they automatically populated? The material view is it?
Yes. Yes, it is. That's right. Please.
You have a heuristic, let's say, for when you will stop scaling up a single node ClickHouse and you think of adding more nodes to the cluster?
Oh, I think I did not get your question.
Let's say you start with one node of the ClickHouse.
Yeah.
And sometimes you have more data, you need more performance, and you
Yes.
start scaling that node up. When is the time to start distributing the load?
Well, actually, general answer is first of all you need to scale up. Like it's cheaper to add more hardware and more CPU to a single server. If you're INS, like if you're limited by something, after that you add another one shard or another one replica and scale not vertically but horizontally. So that's usually what you do.
That is a heuristic or something that is at a tipping point and you say that now I have to have nodes or more shards.
Usually it's about your business. So if it's okay for business to wait for queries, you can even have one node like forever. But like if you have some UI that people are coming to, you have to like decide how fast it's okay for your reports or whatever you're building to render.
Doesn't it depend on the size of your data?
It's kind of like it depends obviously, because more you scan, the slower it is. Like if you're like limited by I/O. But in general, it usually comes from like what your product is and what your expectations from this product are. So for instance, compared to, for example, to MapReduce clusters, ClickHouse clusters are often like underloaded. So they have like extra capacity to really like do it like a spike of like computations and rest for the next query until the next. So it's typical pattern for when requirements for like latencies are like really high. But sometimes they're not.
When you scale up, there will be any repartitioning of the data or not? I mean, there will be data moving around.
No, we do not
Scale up
automatically partitioning actually. But what you can do, you can enable setting for distributed table. It's usually replica priority, and you can say that for concrete replica we insert more data than for all the ones, and that's what we usually do in Yandex Metrica actually. But it's not easy to automatically rebalance data. More questions?
Let's hold it for 9 and go out for. So thank you very much for coming.